this concept of stationary points, then we must first of all spell the concept of partial fractions, partial differentiation in details, okay? So in partial differentiation, there are three kinds of differentiation. We have the 3Ds which are used to denote the derivative. So if you have this D, that D is for the ordinary derivatives, isn't it? When you have this D which is bending, that D is for the partial derivatives, isn't it? Then when you have this D which looks for like S, this D is usually used to denote what? Changes, or just small changes, isn't it? So if somebody tells you to find the change in T, you'll see they will denote it like that, change in T. Are you seeing that? Find the change in S, change in S. Are we together? So this D, which looks like S complete, is used to denote a change or small change in something. Are you seeing that? Then this D, which is bending, is used to denote the partial derivative. Then this other one is used to denote the ordinary derivatives. Are you seeing that? So, in ordinary derivatives, maybe when you have maybe a y to be a function of x, when you have y to be a function of x, it's like saying y is 2x squared maybe plus b, meaning y is in terms of x, isn't it? So in this case, if you want to differentiate y with respect to x, you get dy over dx. That is the ordinary derivative. You see that? So this ordinary derivative in that y is a function of x. If you want to denote y, the derivative of y, it is just denoted as y prime or f prime of x. You see that? Are you seeing how to denote an ordinary derivative? The derivative, ordinary derivative is denoted by prime. So if you are doing successive differentiation, meaning if you are doing it for the second time, it becomes f double prime of x, isn't it? If you are differentiating it for the third time, it becomes f prime of x. Are you seeing that? That is ordinary derivative. Now this partial derivative, why are you doing partial differentiation? You are doing partial differentiation because you have more than one variable. Are you seeing that? So maybe you have a case like maybe z to be a function of x and y, isn't it? So if z is a function of x and y, it's like you be told maybe, for example, z is x squared y plus 2x plus 3. You see this case, plus 2x plus 3 maybe plus 3y squared. So you can see z is expressed in terms of x and y, so it means it is a function of x and y, meaning x and y are the variables. The quantities they are varying. Can you see that? Are we together? So in this case, when you want to perform an ordinary derivative, when you want to get dz over dx, this one, if you want to differentiate with respect to x, meaning both x and y are considered to be variables because of ordinary derivative. You see that? Meaning if you are differentiating this x squared y, you now see it as a product of two variables. Do you see that? So you use the product law to differentiate it. Do you see that? The product rule. Are we together? Because it is a product of two variables. Because of the case of ordinary derivative, this one is now a product of two variables. Now, what about a case of a partial derivative? Meaning you want to differentiate z partially with respect to x. Use that for denoting a partial derivative. You see that? So if you now want to differentiate it partially with respect to x, it simply implies only x is a variable, anything else is taken as a constant. Are you seeing the difference? Only x is a variable and anything else is taken as a constant. So the moment you are differentiating x squared y, this y is no longer a variable, it is a constant because partially with respect to x, meaning you only take x as a variable. Any other thing is now a constant in that case. Are you seeing? Then when you want partial z with respect to y, meaning in this case only y you consider a variable. Anything else is a constant. So you see the difference between doing the ordinary and the partial. Do you see that? Ordinary considers everything as a variable in cases of the variables listed there, isn't it? But partial, only that variable we are differentiating partially with respect to is the variable. Anything else is a constant. Do you see that? Now, we have to understand this concept of partial derivative and how to denote it there. concept of partial differentiation. So the partial differentiation, to understand this concept of partial differentiation, the first thing you need to know is how to denote a partial derivative, isn't it? So there are two different ways of denoting a partial derivative. Because when we are going to deal with stationary points in two variables, we are going to use the partial derivatives. Are you seeing that? When we are going to deal with stationary points in two variables. Are we together there? So, this partial derivative, we are going to employ two different methods of finding the stationary point. One method, we are going to use the method of the Hessian matrix, and on the other side, we are going to use the method of the discriminant. Then we see what is the relationship between the discriminant and the determinant of the Hessian matrix, so that we see which method do you feel comfortable with to define the nature of a stationary point. Are you comfortable defining the nature of a stationary point with the determinant of an Hessian matrix, or where you use the principal minimums, or are you comfortable to define the nature of a stationary point with the discriminant? Are you seeing that? Are we together? So, if you have Z to be a function of x and y, then the very first partial derivative you can get here, you can differentiate z partially with respect to x, isn't it? So if you differentiate z partially with respect to x, it is denoted like that, isn't it? So this is then one of the ways of denoting. We say when we are differentiating z ordinarily with respect to x, it is like this, isn't it? And that one can be known as f prime of x, isn't it? Now, what about if we are differentiating z partially with respect to x? Now, instead of f prime, which implies ordinary, for the case of partial, it is f subscript x. So, when it is subscript x, it means we are doing partial differentiation with respect to x. Are you see? But when it is prime, it means that is ordinary. Are you seeing the difference? But at the end, this is a derivative, this is a derivative. Meaning this one is partially with respect to x, but this one you just differentiated the first derivative with respect to the given variable. Are you seeing that? Are we together? So it means the moment you are looking for this partial z partially with respect to x is the same as f subscript x, meaning we denote because z is f. It's the function of x and y. Are you seeing that? So it means you are differentiating z partially with respect to x is denoted in form like this. Is that okay? So from this derivative, you can get two more derivatives. The first one, you come here. For the first time, you differentiated it partially with respect to x. Are you seeing that? For the second time, you can do it again partially with respect to. Are you seeing that? Successive differentiation. Is that understood? The first time you differentiated partially with respect to x, and you want now to, this one you differentiated partially with respect to x, is now you are differentiated for the second time. You are now doing successive differentiation. Are you seeing? You are differentiated for the second time partially with respect to x again, meaning this one is going to be the same as partial squared z over first time you did with respect to x, then with respect to x again, meaning over partial x squared. So it means this notation is the same as that. Are you seeing that? Are we together? Oh, here you can see, the first time you differentiated partially with respect to x like that, isn't it? Then the second time, you will now want to do it partially with respect to y. You put that as a subscript, you show partial differentiation. Ordinary is prime. Are you seeing that? So this one is the same as what? You come, it is now partial squared z. Squared means you've done differentiation twice. Are you seeing that? So, over the first time I did it partially with respect to x, then the second time I'm doing it partially with respect to y. Are you seeing that? So it means when you perform a partial differentiation with respect to x for the first time, you can get two more for the second time, successive. Are you seeing that? Are we together? So it means from here we already have three partial derivatives. Is that okay? Then we go to the second case. If you did the differentiation for the first time partially with respect to y, it is denoted as a subscript. Are you seeing that? Are we together? So if you differentiated z partially with respect to y, it means it is yf subscript y, which is the same as what? We've differentiated z partially with respect to y, meaning when you have this derivative, you can differentiate it for the second time partially, isn't it? Are we together? So if for the first time I differentiated partially with respect to y, this one was this first time, isn't it? Then I now want to differentiate this for the second time with respect to y again. So it is f by y. Are you seeing that? So I've done successive differentiation twice, which means I have d squared z. The first time I did with respect to y, then with respect to y again, meaning dy squared, isn't it? And remember the deviation for the partial, not that d for ordinary, isn't it? Is that okay? Again, for the second one, the first time I did it with respect to y, partial with respect to y, the second time I can now do it partially with respect to x. Are you seeing that? So it means I've done successive differentiation partially twice, isn't it? So if it is twice, it is going to be d squared z, isn't it? Then over the first time I did it partially with respect to y, the second time I've done it partially with respect to x. Is that okay? Good. So after doing this, you can now see we have the six partial derivatives. Now these 6 partial derivatives is what is going to help us to determine the stationary points in 2 variables. We are going to use them, which ones give us the stationary points and which ones give us the nature of the stationary point. Are you seeing that? Are we together? So once we have these ones, the first thing you will do, if you have stationary points in 2 variables, is what we are interested in 2 variables, stationary points in 2 variables. How do we get a stationary point, if you can recall? What did you say? At the stationary point, the derivative of a curve is 0, isn't it? Remember, when we are looking for the derivative of the curve, it is this first derivative, isn't it? But because we are doing we are dealing with partial differentiation, meaning there are 2 derivatives. This is the derivative and this is the derivative. Are you seeing that? The derivative of the curve is 0. The first derivative. Is that okay? Are we together? So write that at the stationary point. At the stationary point, the derivative is 0, isn't it? So if the derivative is 0, meaning at the stationary point, it simply implies either this is 0 or this is 0, because there are 2 partial derivatives, isn't it? So that implies that it is either this partial z over partial x, which is equals to 0, or this partial z over partial y, which is equals to 0. Are you seeing that? Or you can say the derivative f subscript x, which is 0, or f subscript y, which is 0, because this notation, this one is the different way of notation, meaning we are going to use 2 different methods. So we see a method whereby if you feel comfortable with this, we deal with that with the discriminant, isn't it? Then we see a method, if you are comfortable with this notation, we deal with that with the determinant of the Hessian matrix, isn't it? Are we together? So, after now, when you now get these derivatives and you equate to 0, meaning you are looking for the stationary points. So at that point, you will be solving simultaneous equations. They will not all necessarily be linear, they will just be simultaneous. Some of them will not be linear, isn't it? So you will be solving simultaneous equations. So when you solve the simultaneous equations, you will get the values of x and y. Maybe one simultaneous equation can give you the value of x, isn't it? Then now you use that value of x in the next equation to get the corresponding values of y, isn't it? So that maybe if at x is equals to, you found where x to be 2. When you substitute that 2 in the next equation, you get the corresponding values of y, isn't it? So that you are able to get points in the form xy, xy. And those points are the stationary. They are the stationary point because it was at the stationary point which gave you those equations, isn't it? Are you seeing that? Now that you've now seen a way of getting the stationary points, then the next question you ask yourself, how do I now state the nature of this stationary point? Are we together? How do we state the nature of that stationary point? Nature of the stationary points. Now, stating the nature of the stationary point, there are 2 different methods. The first method we want to see, because it is that first method which is good when you master it, is when you cannot confuse dealing with the discriminant. Are you see that? So the first method, we are going to deal with the Hessian matrix. Now, when you deal with the Hessian matrix, the first thing you have to know is how to construct an Hessian matrix. Are you seeing that? You have to know how to construct an Hessian. Constructing an Hessian matrix is very simple. An Hessian matrix is just a square matrix of second order partial derivatives, meaning these are the second order partial derivatives, these four, meaning these four second order partial derivatives are the ones which are forming the elements of the Hessian matrix. Are you seeing that? It must be a square matrix. It can be a 1 by 1, a 2 by 2, but when it is a 1 by 1 matrix, what does that mean? It means your Z was a function of only one variable. Are you seeing that? When it is a 2 by 2 matrix, it means your Z was a function of 2 variables. Are you seeing that? When it is a 3 by 3 matrix, it means your Z was a function of 3 variables. Because the Hessian matrix must be a square matrix, and those elements of these elements of the Hessian matrix, this second order partial derivative, they must be constant. Why are they going to be constant? They are going to be constant because the stationary points you've already found. So you substitute those values. Maybe if this value here you found it to be 2x. See, you found a stationary point, for instance, 1, 2, isn't it? So if this partial derivative was 2x, see, you say at this stationary point, f of xx is equals to what? It's equals to 2 because it is 2 times x and x is 1. So 2 times 1 you get 2. Meaning at this stationary point f of xx is 2. So you can see it's a constant. Meaning those elements of the Hessian matrix are constant because you have the stationary point. You will be substituting the values of those stationary points if in case any of these second order partial derivatives was not a constant, isn't it? Are we together? Now, how do we construct an Hessian matrix? You go back to your function. So you had Z to be a function of xy, and we know this Hessian matrix is a matrix of second order partial derivatives, isn't it? So in a real sense, we are not interested in the Hessian matrix. We want to use the determinant of the Hessian matrix, isn't it? Meaning if you know a matrix A, if you want the determinant of a matrix A, the determinant of matrix A is denoted like that, isn't it? Now we now want the determinant of a Hessian matrix, meaning the determinant of a Hessian matrix is going to be denoted like that. Are you seeing? So the determinant of the Hessian matrix is going to be what? If Z is a function of x and y, 2 variables, meaning it is what? It implies it is a 2 by 2 matrix, isn't it? So in this 2 by 2 matrix, we have 4 elements, 2 by 2, isn't it? So you put your F's, F, F, F. Then now look what is happening here. You see here, F is a function of x, y. X comes first, the order of a matrix. If x comes first, it means the order of a matrix will define a row first, followed by a column. Are you seeing that? So if x comes first, it forms the first row. So the first row is x. Then y comes second, it forms the second row. Remember, rows are the horizontal arrangement, isn't it? Are you seeing we define the rows? The first row and the second row. Then after defining the row is when you now define the column, isn't it? Are we together? So when you are defining the column, x comes first, meaning x forms the first column. Are you seeing that? So the first column will be xx. That is the first column. Are you seeing? Then y comes second, y forms the second column. So the second column is that yy. Are you seeing? You key in the elements of the Hessian matrix. And you can see f of xf, f of xy. You can see them here. You have them here. Are you seeing? Are we together? So by the moment you define this, you are now looking for the determinant. Remember, I'm not putting it in bracket like that for a matrix. I'm putting the strokes to show that it is the determinant we are interested in. Are you seeing that? Are we together? Now, if you look at this, what do you see here? What is the determinant? The product of the elements in the main diagonal minus the product of the elements in the other diagonal when you have a 2 by 2 matrix, isn't it? So the determinant here is what? This times this. It is f of x, f of y, then minus that times that. And what did you note when you started with this partial differentiation in calculus 1? You noted that this is always the same as this. If you start with x, then followed by y, or if you start by y, then followed by x, they will give you the same thing. Isn't it? Are we together? Then this times this minus this times this, f of yx times f of xy. Isn't it? But this is always the same as symmetry, isn't it? It's always the same as that. When you start with y followed by x, or when you start with x followed by y, you get the same thing, isn't it? Are we together? So this one is like saying it is f of xx, f of yy minus f of xy squared. Because this and this is always the same. Is that okay? But there's no need of doing that. We have the values here with the constant, meaning we'll be getting a constant value from there on the spot. I'm only using this because I want to explain something, okay? Are we together? So the moment you get this determinant of the Hessian matrix, it is now what is going to define the nature of that stationary point. Now, here, when the determinant of the Hessian matrix is greater than 0, when the determinant of a Hessian matrix is greater than 0, then it implies a turning point. When the determinant of a Hessian matrix is greater than 0, then it implies a turning point. Are we together? So it means the moment you get it to be a turning point, then there are going to be two cases. It means when the first principal minimum, the one you start there, 1 by 1 matrix, is this f of xx. Are you seeing? Are we together? When the first principal minimum is less than 0, then it implies a what? A maxima, isn't it? Then when the first principal minimum is greater than 0, then it implies a minimum, isn't it? So when the first principal minimum is greater than 0, then it implies a minimum. So look here. Look here. What has happened here? You now want to see why this one is very different with the discriminant, so that you don't get confused. Are you seeing that? Then, when let us first of all complete. When the determinant of the Hessian matrix is less than 0, when it is less than 0, then it implies what? Shadow point. Meaning when it is equals to 0, then there is no, it is an undecided scenario. You cannot make a conclusion. Are you seeing that? Are we together? Now that is the first case of checking the nature of a stationary point. Anytime you see the Hessian matrix to be greater than 0, then it is a turning point. Now look at the second case. The first case in the nature was the way it was using through the Hessian matrix. Now the second case is now through using the discriminant. The discriminant denoted by delta. How are you going to get the discriminant? The discriminant is very easy. That's why I wanted you to know how to construct an Hessian matrix, because you will forget the formula of the discriminant. But Hessian matrix can help you to know the formula of the discriminant. Are you seeing that? Are we together? Because constructing an Hessian matrix is very easy. So the moment you construct an Hessian matrix and you see this, then it means you can use this to get the discriminant. Are you seeing that? So the discriminant is always equals to the negative of the, is always equals to the negative of the determinant of the Hessian matrix. Are you seeing that two different things? The discriminant is the negative of the determinant of the Hessian matrix. That means the discriminant is going to be what? If the Hessian matrix was what? F of xx, f of yy minus f of xy squared. Meaning the discriminant is going to be negative of this. Meaning you are now going to start with this. Are you seeing? Are you seeing? Discriminant is negative of the determinant of the Hessian matrix. But what is the determinant of the Hessian matrix? What did you get? You get the determinant of the Hessian matrix to be fxx, fyy minus f of xy squared. That was the determinant of the Hessian matrix, isn't it? But we can see here clearly that the discriminant is the negative of the determinant of the Hessian matrix. Meaning if you take negative inside the bracket, then you will see that the discriminant is now starting with this. Because negative is supposed to, then negative this now changes this to negative. You see? So you see the discriminant is now taking the opposite. You see the two different things. So it is f of xy squared minus f of xy minus f of xx, f of yy. When you take the negative inside it, you rearrange, isn't it? So that negative, that you now start with that one. If negative goes inside that bracket. Are we together there? So look at this. Now if you expand this, what do you see to be the discriminant? You see the discriminant, this one expanded, it means you differentiated z first time partially with respect to x, then partially with respect to y. Then the whole of it is squared, isn't it? Then it is minus, this one means you did partial differentiation twice with respect to x, isn't it? Meaning this one is, you differentiated twice for the first time you did with respect to x, and with respect to x again, meaning x squared, isn't it? Are we together? Then it is times f of y, which means you differentiated it twice with respect to y squared. So are you seeing how to define a discriminant? Are you seeing it is the opposite of this? Are we together? So what does that imply? It implies when you want the nature of the stationary point, if the discriminant is less than 0, then it implies a turning point. Now look at that difference. Why? When the Hessian matrix is greater than 0 is when it is a turning point. But the discriminant is negative of the Hessian matrix. Meaning if you got the determinant of the Hessian matrix to be 4, you can see 4 is greater than 0. Are you seeing? See, that is a turning point. But now, the discriminant is negative of the determinant of the Hessian matrix. Meaning, when the determinant of the Hessian matrix is 4, it means the discriminant is negative 4. Are you seeing? And when the discriminant is negative 4, see, negative 4 is less than 0. So it means the moment the determinant of the Hessian matrix is greater than 0, the discriminant is supposed to be less than 0. It is the opposite. Are you seeing that? So it means when the discriminant is less than 0, then it is the turning point. But when the determinant of the Hessian matrix is greater than 0, it is the turning. Are you seeing the difference? Because the discriminant is the negative of the determinant of the Hessian matrix. Are we together there? So when you want to define the nature of a stationary point with a Hessian matrix, then the determinant of the Hessian matrix must be greater than 0 for you to get a turning point. Are you seeing that? But when you want to define the nature of a stationary point with a discriminant, then the discriminant must be less than 0 is when you get a turning point. Are we together? Both this one is greater than 0 and defining a turning point, this one is greater than 0 defining a turning point, but this one is less than 0 and defining a turning point. Because y is negative of the r. So that is the reason why we say, if you want to use the discriminant, you must know how to get the formula of the discriminant. The formula of the discriminant will only come out if you know how to construct an Hessian matrix, isn't it? Are you together? So it means when you are using the Hessian matrix, the determinant of this must be greater than 0 is when you get a turning point. But when you want to use the discriminant must be less than 0 is when you get a turning. Are we together? So the moment you get the discriminant less than 0 to define a turning point, then you now use the first principle minimum is now what? Partial squared z with respect to x. When it is less than 0, it is what? Maximum. This one remains the way it is as always. What is different is the discriminant and the determinant of the Hessian matrix, isn't it? But you know when the first principle minimum is less than 0, it is always a maximum point, isn't it? When the first principle minimum is greater than 0, it is always the minimum value. Are we together? So when this one is the first principle, that is the reason why I was starting by giving the two different notations, so that you see the notation which are comfortable with the Hessian matrix and the notation which is comfortable with the discriminant. Are you seeing that? So from here you now get, this one now implies the maximum point or maximum value in that manner, isn't it? Then if you have the first principle minimum to be greater than 0, that is always the minimum. The minimum what? The minimum point. So what does it mean? It means when the discriminant is greater than 0, it implies what? A shadow point, isn't it? So when discriminant is greater than 0, then it is a shadow point. So here you have to be very careful. This one is the opposite of the other. They are not the same. Are you seeing that? Are we together? One is the opposite of the other when you are defining the nature. Okay? When the Hessian matrix is greater than 0, that simply implies discriminant is less than 0 because the discriminant is the negative of the determinant of the Hessian matrix. Are we together? Good. So that is how to find the stationary point, and that is how to state its nature. Are we together? So can we now see the first case on that?